So just a quick heads up, this is it starts off kind of abstract and I try to make it a bit less so than usual. It's not really the best thing to learn abstract maths this overnight. So to spare everyone a bunch of long drivel proof, I decided to forego most of that and just stick to the main points. So let's get started. As you can see, typically gives it away, computing the nearest correlation matrix. This can actually be done in any kind of field that uses any kind of correlation relation. But because my background is in finance and statistics, I use it in a finance setting. So for those of you who are interested in finance, I can show you at the end an application that I use in a risk management setting. So let's see. So first I'll go through an outline of the presentation. Start off with some simple linear algebra concepts, just to set the stage of how we build up to the actual algorithm. Then we go on to the original theory, which the algorithm stems from, which is called projection theory. For those of you who work with a lot of matrix algebra, I'm sure you all are aware of this. It comes from a guy named von Neumann. He's a pretty well-known guy. So I'm sure anyone who has done maths or any kind of applied statistics or computer science will know about him. And then finally, I actually introduce the problem and the algorithm, and I show you one application of one instance of it. And then at the end, I will show you the final application I did in my actual dissertation. So I'll just switch screens quickly after that. And then I'll end by mentioning a couple of outstanding problems that has to do with this particular approach. Okay, so feel free to stop me anytime. It's a pretty short presentation because, like I said, the majority of this entire thing stems from building up the algorithm through a bunch of matrix algebra and proofs. And like I said, I decided to forego all of that. But if you want to see it, I can give you some ideas. So you start off with some linear algebra. And it's basic stuff because everything, as you all know in algebra, takes place in a vector space. And in this case, we're going to stick to real numbers. So we're just going to stick to the span of vectors that go over all the real numbers. And then we're going to work within a particular vector space called a subspace. And the idea lies in the name of it. A subspace is simply a subset of a whole vector space. And you take any linear combination of two vectors, which is in a subspace W. And if that linear combination remains inside of W, W is a vector space, is a subspace, sorry, of the entire vector space V. This is not the pure technical definition, but this is just the idea, which I build up to after a while. So just keep this in mind. Any linear combination of vectors within W, which lies within W, would be a subspace of the entire vector space V. Okay, so again, just stop me if you think I'm being too fast with the whole W and V stuff. That's just the nature of this algebra business. So when you're comparing vectors, you need to have some kind of metric, right? And everyone who has done A-level maths, all of you suppose know this, that we compare two vectors with some kind of thing called a norm. Well, a norm is really just a metric that acts on one vector alone. But a more general version of a norm is called an inner product. And an inner product is really any function, any real function that acts on a pair of vectors. Okay, so as you can see, we have two vectors here, x and y. We have three vectors here. And these are just the four main properties that any inner product must satisfy to be considered such. Okay, so like I said, it's purely some self-explanatory. You guys should be familiar with this. But if we focus on one vector, right, we get the norm. Okay, and you can see that the norm satisfies a lot of the same properties of the inner product. I'm sure you all know about this one. It's like the triangular inequality, right? And for this part, this is how we build up to the theory of projections, because you need some way to actually quantify the nearest vector that you're trying to compute. Otherwise, you can just find any vector and call it a solution, but it may be very far away from the actual original problem you started with. So to do this, you start with a norm. Okay, so just keep that in mind. A norm is any real function that acts on a vector, and it gives you out a number at the end of it. Okay, So we're going to stop with the vector spaces and stuff because this is pretty much all you need to know to keep in mind the projection at the end of the theory. So we're going to go on to some eigenvalues, right? So in particular, we're going to go on to this theorem called spectral decomposition. And it's really just taking any n by n matrix and decomposing it into a product of its eigenvalues and eigenvectors. Again, all of you should be familiar with this. It's a pretty well-known theory in applied maths. And in particular, it's used for one, in this particular instance, it's used for two things. It's used to check if a matrix is something called positive definite, and it's used to obtain another one of the projections later on that you will see. So keep in mind this here, because you may see it, you will see it back just now, right? This lambda here is a diagonal matrix, which each diagonal entry representing a distinct eigenvalue. And Q is simply n by n matrix of the eigenvectors. This is Q transpose. Okay. The ith vector corresponds to the ith eigenvalue here. And that is simply the spectral decomposition of a matrix E. Okay, so that's pretty much the entire basis of this projection theory. So we're going to start off with, we're going to introduce it basically. We're going to start off with what is a projection. A projection is basically any matrix P such that when you take P squared, you get back to P. So think about how a projection works in real life. You know, you shine a light on something and you get an image somewhere else. That is pretty much what you have to keep in mind when you think about projections in matrix forms, right? Because a matrix is simply a transformation of a vector. It's a rotation and a translation in different directions. So I actually included a kind of image here so you can see. We have the subspace here, X, and we have a vector outside here, or we have a point outside of the subspace. And the idea is you want to project this vector or onto the subspace and get a solution, X hat. Now, by definition of the projection theory, and Von Neumann showed all of this, I alluded to all of this in the presentation, but this vector here, X hat, will by definition be a unique one, a unique solution, and will be the closest solution to X. This is all shown in the maths, the long, confusing maths for the proof, but you can just take my word for it. X hat represents a unique and closest solution to the original vector X outside of the subspace. Okay. So this is simply a way of saying what I just said. We take the solution W to the projection of X onto the subspace V, such that X minus W is minimized. So this here will just be a vector. You take the norm of that vector and you get the smallest possible norm, which stems from the projection. Okay. So projection theory, Von Neumann showed that instead of projecting directly onto a subspace, it's easier to project onto the intersection of two subspaces in an alternating manner. So instead of one subspace here, this picture we have two, and they're intersecting in some manner, and you just project it onto each one in an alternative way. So this is what this expression here gives. You have two subspaces, U and V, okay? And you have some initial vector, x0, that is outside of the entire V and U, and you just take alternating projections onto them, and you generate a sequence of x's. And eventually, as n goes to infinity, that sequence converges to x star, which is inside the intersection of the two subspaces. And by definition, x star satisfies this expression here and minimizes the distance from the original solution. Okay, so that is the idea of finding the nearest correlation matrix. The idea is that we start from an original matrix, and this matrix is damaged in some sort of way. Again, I will elaborate on this a bit more later. And we want to find the closest matrix that nearest approximates the original one. So I'll get back to that now. And, now I'll actually talk about the solution to the problem I'm referring to. So correlation matrices are special in the sense that they have to satisfy some criteria. And as a result, again, this is a bunch of other proofs that I left out, but correlation matrices, they don't necessarily make up subspaces, right? They make up what you call convex sets. And a convex set is, if you recall the definition of a subspace, where is it? It's a linear combination of vectors, right? A convex set is pretty much the same thing. You take a bunch of points inside the set. Let me just get back to it. Right, so you have a set C, a convex set, and you take a bunch of vectors inside of it, a linear combination of vectors. And if that linear combination lies inside of the set C, then you know there's a convex set. The difference is, however, these scalars are between 0 and 1. Okay, so for the original subspace, the scalars could be anything really. But for a convex set, the scalars are bounded by 0 and 1. And that is what makes up the set of all correlation matrices. To be a bit more technical, it's a convex cone, actually, but this is enough to actually know about why we need to modify the original projection theorem. We're projecting onto a smaller area. Rather than the entire subspace, we're focusing on this limited area here. To be more exact, like I said, a convex cone, which is scaled by scalars between 0 and 1. Okay, so to reiterate before I go on to the final section, we have convex sets, which make up the set of correlation matrices. We have a correlation matrix, which is not valid, and we want to find the closest solution to that correlation matrix, which is in the intersection of two convex sets. So how do we do that? Well, like I said, we make use of the projection theorem by alternatively projecting onto each convex set. And eventually, as the number of projections go to infinity, to the limit, obviously, you get a unique solution, which best approximates the original correlation matrix. So this is just to elaborate some correlation matrix some definitions. A correlation matrix, it must be between -1 and 1, all entries. All diagonal entries must be 1 because obviously a variable correlates perfectly with itself. And this here, it must be non-negative definite. And this is a property that stems from the eigenvalues of the correlation matrix, which is why I went through the whole spectral decomposition earlier on, right? So it's a way to test this last value here. You simply find all of the eigenvalues, and if you see at least one that's negative, you know that the correlation matrix is faulty, and it must be corrected in some way. Okay, so these are all 3 criteria for it. Now, like I said, we have to approximate A by finding a solution X. A will be known as the observed matrix. This is what we get from when we calculate what we calculate from our data. Okay, and we have to take A and project it onto the intersection of convex sets, and hopefully we obtain X within a finite number of projections. So how do we do this? Well, first we have to define the convex sets, okay, because they have to satisfy certain criteria in line with the correlation matrix here. Okay, so we find 2 convex sets. S will be the set of all matrices, M by M matrices, which are all non-negative definite. So all of these matrices here have eigenvalues when you obtain them, no negative eigenvalues. This here implies non-negative definite matrices. And then you have the set U with all M by M matrices with diagonal entries of 1. Okay, so it's the hope that when you find a matrix in the intersection of these two, you get a matrix X, which satisfy all of these criteria here, such that X closely approximates A. A is the observed matrix, remember that. So we take the projection theorem, we use the same thing, and we have to adjust it in some way. Okay, so we project it alternatively onto the sets. This is just the image I took from Wikipedia. So we have the original matrix here. We start with the projection. We project here again, and then you keep doing it in an alternative manner until you get the solution X. X lies in intersection here. And by definition, as I said, X is the closest matrix. How close that matrix is, it really depends on the original matrix, but it is the closest one. So this is something that we can do with the solution that keeps up with practice. We can actually weight the original matrix. What does that mean? Well, remember, these things are observations. So naturally, there will be some kind of error associated with it. So we can take a matrix W, this is known as the weighting matrix, and you can actually weight each individual variable according to how confident you feel that they are measured. So for example, you want to weight between 0 and 1. The more accurately measured a variable is, you will assign a weight closer to 1. So we can do this, and you see W is a diagonal matrix. We can do this, and we can still obtain a solution to A, because this transformation here does not alter the solution at all. I think it's called congruence. Maybe someone can correct me on that. So this solution is still a solution to this, even after you adjust A by this amount, by these two matrices here. So keep that in mind. Okay, so now that we defined our sets, S and U, we have to define the projections onto them. So we have two different expressions for projection onto U and projection onto S. So because we're taking W as diagonal, we can take the projection of U from A onto U as just A, and replace all diagonal entries by 1. This will differ if you're taking a different W matrix rather than diagonal, but for now, we're just taking diagonal. And we're just replacing all the diagonal entries of A with 1. Now, with the S projection, it's a bit more complicated, the proof that is, but this is the expression here. And all that this is saying is that we're taking A, we're weighting it by the W matrices, we're taking the spectral decomposition of it, recall the initial theorem, and we're replacing all of the negative eigenvalues with 0. So we're taking either 0 or the actual eigenvalue, and then we're applying these two weights here to it. So again, like I said, this is a bit abstract, and the application isn't that enlightening in the sense that you literally just run the code and you get a matrix at the end of it with a metric. But it's a pretty cool way to actually correct, a broken correlation matrix. There are other ways which I may mention at the end of this, but this is the one I worked on. So now onto the actual algorithm. So I should have written this here, but this is an actual modification of the original projection theorem. And like I said, it's a modification because rather than projecting onto subspaces, we're projecting onto convex sets. So the guy who came up with this modification is called Dijkstra, and he introduced a correction matrix, which starts off as a 0 matrix. And we say that 0 starts off as a 0, and Y0 starts off as A being our observed correlation matrix. And you can see this is the entire algorithm. We start with K here, and then we subtract the 0 matrix on the first iteration. We take this matrix, which is a result of the R here, onto the S projection. And then we update our correction matrix here for K equals 1. And then finally, we project onto the U. Now, this here will continue as algorithm does, and it will produce a sequence of two matrices, Y's and K's. Now, either one of these sequences can be used to test for convergence. The idea is that as these two converge, they will converge to the same solution. So the difference between both of them will slowly approach 0 as n approaches infinity. So we can use this expression, which is pretty much like the rate of change of the matrix. You can think of it as You're taking the rate of change of y of x over the initial position. And this approach is zero, as both of these approach the same solution. And that is pretty much it. You can use any norm to test for it, but the generally accepted norm for this is called the infinity norm. And the infinity norm is pretty much you take a matrix and you take the max row sum of it. And that is the best norm that Dijkstra used to test for this convergence here. So I can show you an example. Yeah. So let's say we have A being our correlation matrix. This is clearly wrong because first of all, you have 2 is a diagonal. I purposely made this very wrong to show you the algorithm. We take Y, we take W to be the identity matrix. This can be adjusted to reflect any kind of weights that you choose. Okay. And we apply the algorithm. And you can see after 18 iterations, not very fast, but I'll get to that in a second, we obtain this corrected matrix here. You can see that diagonals converge to 1, and all of the elements are bounded between 0 and, -1 and 1. And you take the norm here, and you get this is the distance between A and X. Or F stands for Frobenius norm. Frobenius norm is pretty much the matrix version of the standard Euclidean norm. Okay, so I can actually show you in my actual dissertation an application in finance in general. So, like I said, this can be used for any. Oh, by the way, this is the actual proof for one of the proofs if you're interested. So it's just a bunch of matrix algebra. But I'll just skip over that. Okay, so before I go over this, like I said, this is a correlation matrix. It pops up in any area of multivariate statistics. So it can be used regardless. Okay, I just use it in a financial application. So for those of you who know, the correlation matrix is one of the main ways of optimizing your portfolio because it shows the relationship between your portfolio of assets. Okay, now now you want to have something called diversification in your portfolio, which means that you want to have a lot of opposite correlations. So in case one stock goes bad, the other stock may go good. Okay, so that's an idea of what this is used. It's called mean variance optimization, and it was introduced by Markowitz, who pretty much started off the idea of portfolio optimization using the correlation matrix. So I will skip past this, but I want to show you basically how the idea of a broken matrix comes about in financial applications. So let's say we have a matrix of stocks. In this case, I have Apple, Amazon, Sony, Nintendo, Microsoft, all fairly large companies. So I just chose them because of convenience. But let's say you have a portfolio of thousands of stocks. Now, you're bound to have a bunch of them that won't necessarily put out observations or put out data on the same day. So let's say in the case of Apple, Apple puts out data on a daily basis, right? It's a fairly big company, it can do that. But let's say you have another big company. Let's say Amazon in this case, is a new company and it's just getting started. It's probably in its less than 5-year business operation. And Amazon may put out data on a different basis. It may put out data on a weekly basis. And if that's the case, for let's say for Apple, you will have data coming in every single day, right? Now for Amazon, you'll have data coming on a weekly basis. So automatically you can see that you will have different length time series of price data. And if you try to calculate the correlation between Apple and Amazon, you'll get a correlation metric with a very big error bar around it. And that is what essentially causes the matrix to be bad. You have a lot of errors surrounding the individual pairwise correlations, and that can cause the correlation matrix to be faulty. So for this application, I purposely chose the time series to be of differing lengths. This is done to illustrate the point I was just making. And you can see a snippet here of how the data looks. So Nintendo here puts out price data like that. We have Amazon here puts out price data like that. And you can see that for the dates, they don't have corresponding data points. So you can see that any correlation metrics between Nintendo and Amazon would be very poorly measured because automatically you're seeing that they don't have plenty matching points here. Same you can see it for Microsoft and Amazon or Nintendo and Apple. Okay, so the idea is that this happens a lot in practice because of the sheer size of the portfolio. Okay, this is just a portfolio of 5 assets, so very scalable and very forced. But if we calculate the correlation matrix for this, you'll see that it's non-positive definite, which means that somewhere here, there's a negative eigenvalue. And you can see here that there's a value that's lower than -1. It's almost -2. Okay, so one time this is not a correlation matrix. So after running the algorithm again using W as I, the identity matrix, we find that the closest matrix to the observed one is only 1.7 distance away. I don't know the exact distance, and we get this correct matrix. So that is the idea behind this. Now, W, like I said, can vary. You can, for now, it's generally the norm to stick to the diagonal matrix, but it doesn't have to be identity. You can actually vary W, the weights accordingly. And I think I did that. I did that here to show you a point. And that is one of the drawbacks of this method, right? If you use the identity matrix, all of the correlations change, even those that are measured, totally measured accurately. Okay, so let's say we have the correlation between Nintendo and Microsoft, right? You can see this here was 0.746. It changed quite a bit actually. It's still a very high. It still kept the direction, but it changed. Okay, so this can actually be done for anyone, and it can actually greatly inflate the degree of relationship between two variables. So you have to be careful with that. So that's why you tend to weight the observations to kind of account for this. So I can show you the example of how I did that. So I reiterated here that the correlation between Microsoft and Amazon was 0.746, and it changed to 0.812. And if we weight the matrix, let's say 1, 1, 0.45, 0.1, and 0.45, these here reflect the degree of accuracy of the observed variables. So if you remember, Amazon was here, and Amazon didn't have that much data corresponding with these here. That's why it's 0.1. Okay, so you see that if these are weighted, you can actually preserve the relationship a bit more. The correlation increased to 0.7. It stayed relatively similar to the original one, 0.756, and the original one was 0.746. So that's a bit better. The only downside, however, to this method is that, let me just go back to the original presentation. The only downside to this method is that if we're using this method of weighting the matrix, it's like a linear convergence rate. So the bigger your portfolio, the longer it's going to take. Okay, and you have the added disadvantage of you cannot weight individual observations. You have to weight the entire variable column, as you see with the diagonal matrix. There is a proposed solution to that, however, and it comes in the form of using a different matrix to weight the observed matrix. It's called the H weight, and it stems from the company called the Hadamard product. And if you look at what this is, it's pretty much the pairwise multiplication of each element. So this allows for the individual weighting of each observation within the original matrix. So this has the added advantage of being more flexible in terms of the weighting capabilities. But the downside is that even though it has this form. There is no closed form solution, well, no closed form solution known yet, that projects this weighted matrix onto the S projection. If you remember, we defined the projections earlier on with respect to the W norm. With respect to the H norm, there is no closed form solution in this form here. So that is one piece of area in which research is still going on. Um, there is a solution for the U projection, but not for the S projection. And that is pretty much it in terms of the entire algorithm. Any questions? I know that's pretty abstract in a sense. Sorry about that.
No, this was good, Nishad. I have a question, and there's probably a reason for doing it this way with the projections, but can't you see this as a regular type of optimization problem and use traditional nonlinear optimization approaches? Because you have the objective, right? The objective is to minimize the Frobenius error, right? And you have all the constraints. The constraints are the matrix X has to be conform to a correlation matrix. So you can say those as constraints, and you have the objective, and it's a optimization, nonlinear optimization problem, right? Is that possible?
Yeah, it is possible. Like I said, remember, the set of correlation matrices make up something called a convex cone. So there's something called conic optimization. I'm sure you all are familiar with that. I'm not too familiar with it right now, but that is a next approach to doing this, something called conic optimization.
Okay, because in that case, you could keep all the known correlations fixed, right? And yeah, okay.
There's also next way called shrinkage estimation, and it's more based on the Bayesian point of view. But it's pretty much taking the observed matrix and you're multiplying it by a shrinkage estimator until you pretty much keep shrinking it down until you get to a known form of the correlation matrix.
Okay. All right. Thanks. No, interesting stuff. Thanks.
But that approach has the added hurdle of getting the shrinkage estimator correctly, because it may differ between markets and industries.
Okay. Thanks.
Yeah. Any more questions?
Well, I mean, I have two. I know you were to present last week. So last week we covered a bit of, we did optimization with Enzimum, and how aspects of math is turned into algorithms and then other applications. So here you're doing finance. By dissertation, you mean your PhD is in, you're doing or you've done it?
Oh, I've done it. I finished in 2019. Yeah. So.
What's the field?
Statistics and finance.
Okay. All right. And then a laywoman's question. Could what you've done help us to figure out if we should be buying GameStop stocks?
Not that is more of a personal question. If you think that is more of a okay, so the thing about GameStop right now is that regulator, and this is going on a tangent from this, but to answer your question, GameStop right now is going to be heavily regulated from now on because of what is happening. Okay, and I sure you all saw that this entire thing about the hedge funds losing money because of GameStop. The games and those hedge funds basically bet against GameStop, and because of these Reddit investors, they push the price higher and higher. Those hedge funds are now losing money, and now regulators are trying to step in to limit all of the transactions regarding GameStop and by extension AMC and the other stocks that correlated positively with it. So yes, you can use this if you have a portfolio of those stocks because it will be a correlation matrix. But in terms of buying it, that's more a personal question. That's more if you think that the stock will continue to increase in value, or if you think that the stock is going to decrease in value in the near future, in which case you can short sell. But yeah, hopefully that answers the question.
It did. Thank you.
No problem. Any more questions? It wasn't the most enlightening thing. I should have put more maths in it. I'm sorry.
No, it was good. It was good. Thanks.
Okay, so I guess I'll stop sharing. Thanks everyone for listening.
Okay, so let's thank Nishad for his presentation.
So Nisha, did you publish this work as well?
No, it's not original. Maybe if I come up with or try to work on the outstanding problems, yeah, that could be a publication, but it's not original, unfortunately.
Oh, so what was your contribution then for the thesis?
Okay, so my one was pretty much using it in such a way to come up with something called the market risk of a portfolio. Because I use it in a combination with principal component analysis to break down the portfolio in terms of the individual components, and I focused in on minimizing the market risk of it.
Okay, so your contribution was really applying it to finance in a way.
Yeah, that's what they pretty much wanted from us in terms of the because we had about 2.5 months to do it. So
Okay.
to come up with something new in that span would have been a bit time constraint.
Right.
Yeah.
Okay.